So our next talk is a submitted paper from Yanan Lau.
Yeah.
Perfect. So yeah, thank you for submitting and coming along.
Okay.
You can share your screen.
Yeah. Can you see my screen?
Yeah, it's popped up. Excellent.
Okay.
Excellent. So yeah, thank you for submitting. I hope it'll be interesting. I really want to see this.
Okay. Shall I start?
Yes, please do.
Okay. Hi. Yeah. Hi, everyone. I'm Yanan Liu from the University of Bristol, a PhD student supervised by Professor Wataru. I'm going to talk about my accepted ICRA workshop papers. You may have already know the design principle of the pixel processor array introduced by Professor Dudek. The CNN inference in this work is wholly performed on the pixel processor array, and the servos can be controlled through the GPIO from the ARM M0 controller, and a maximum of 5 servos is supported to set up a more comprehensive sensory motor system. Yeah, as you can see, a servo motor is directly driven by the SCAMP vision system without any additional intermediate hardware. With the machine vision computing results from the SCAMP vision system, the servo can be instructed accordingly. We use our previously proposed binary convolutional neural network for this work. We train a binary neural network offline and implement image convolution, ReLU activation function, max pooling, and fully connected layer for this CNN inference. As you can see, each image here is either in an analog register or digital register, and all the binary weights for the convolution and fully connected layer are stored in digital register. With this architecture, the whole CNN can be performed using very simple and efficient operations, including addition, subtraction, bit operation, and shifting, enabling high-speed CNN inference. This is a demo for 3 hand gesture recognition and for English letter classification using the servo motor as the indicator. For hand gesture recognition application, a stride 2 with a single convolutional layer and a fully connected layer is utilized to achieve a trade-off between the efficiency and the robustness. Our network can operate with a latency of 121 microseconds from image acquisition to classification result available in the microcontroller. Yeah, there's more. Yeah, this is the letter, 4-letter recognition example. And we also propose the semi-simulated platform by integrating the SCAMP with the Coppelia Sim robot simulator. This platform takes advantage of the SCAMP's parallel computation ability and the rich simulation scenes in the simulator, where applications can be exploited and validated virtually. Basically, the simulated sensor readings from the simulator can be transferred to the SCAMP Python host through the remote API, and followed by another transmission through the USB to a real SCAMP. After image processing in the real SCAMP, the useful information can be sent back in the same way to the simulator, where those useful information can control the movement of a robot or simulated robots or something. The image at the bottom is the CNN architecture for localization and tracking application based on the SCAMP. A shared convolutional layer is used for object 2D localization on the SCAMP, where networks for labels indicating X and Y are using identical convolutional layer, but a different fully connected layer. Yeah, the image on the left is the example robot simulation environment. Yeah, the right image shows the tracking trajectories with a drone. There are three passes. The first one is the preset rule trajectory at the ground truth, and then the drone tracking trajectory with the convolutional neural network on PyTorch guidance. Because on the PyTorch, we run convolutional neural network on PyTorch because there's no errors. And then the third one is the drone tracking trajectory with the guidance from the SCAMP CNN inference just for a comparison between the ground truth simulation in PyTorch and the real implementation on SCAMP. Okay, I think, that's all my presentation. Yeah. And yeah, do you have any more questions?
Excellent. Thank you for presenting that. I'll kick it off with a question about the direct servo motors. I just wondered how do you go about actually running them from the device? Is the device already sort of a real-time system that allows you to do PWM, or is there a way we can sort of, do you reckon there's a way we can almost cut the middleman out and have more direct connection between the sensor processor and servos?
Actually, there's a library developed by University of Manchester in the M0 controller. Basically, we can use the results from CNN inference and use the library for PWM to control the motion of the servo motor.
Excellent.
And actually, if we can extend more servo motors. And in that case, we may need other power supply for more servos control because of the power. And in the SCAMP, currently, we just use the GPIO as the power supply for servo.
Cool. Okay. Yeah, so I guess you need to have it part of a bigger system if you wanted to be able to do more, right? It can't deliver enough power by itself. We have a question. How are the networks trained? Do they take into account the noise caused by the analog computation? Is there, what do you do anything, or what do you do to account for that in training?
Actually, we just train the network using binary connect. Actually, it's a little bit independent from implementation from the analog or digital stuff in the SCAMP. We just train it separately and then implement our neural network on SCAMP. And one thing we need to mention is that we introduce some noise as the data augmentation simulating some noise from the SCAMP. Because when calculating with the analog registers, there's a lot of calculation noise introduced. So we use those kind of stuff as data augmentation when we training our binary neural network.
Cool. And one more. How do you go from the original image to your image preprocessing step? So I mean,
okay. Oh, you mean
you've clearly got a lot of data movement there across the sensor.
Yeah.
That become an efficient process to do.
Actually, we do it basically in parallel too. And for this step, basically we just resize this image into 64 by 64 and replicate it to fulfill all the processor. I think this step costs a lot of time compared to other step. Especially if you want to implement something with 64 kernel filters. Currently we are using 16 kernel filter, but if we use 64, maybe we need to do more replication operation.
And is this so I mean, do you think you could say half the number and go for 8, for example, if you So it looks on your convolution step, you've got your weights there in the digital registers. If you had more digital registers, would you be able to store 2 sets of weights for every patch? And therefore you might have to do less pre-processing or more efficient pre-processing.
Sorry, you mean if we need more kernel filters or something?
So you'd be able to have the same number of kernel filters, but larger patches because you have more than one kernel filter per patch. Is that something that seems possible?
Yeah, actually, yeah. If we need more kernel filters, yeah, and basically, yeah, I think we have 2 plans for that operation with more kernel filters. One is to using a smaller images like 64. Currently the image size is 64 by 64. Yeah, if we are using more kernel filters, we have to using a smaller image like 32 by 32. In that case, we can deploy 64 kernel filters. Yeah, this is one solution. Another solution is to do convolution, combine sequential implementation and parallel implementation. For example, if we need 32 kernel filters, we can use this single image, but with 2 digital registers storing those kernel filters and perform convolution twice. Yeah, in that case, we can get 32 filter maps.
Excellent. Thank you so much for the talk. It's really interesting to see where and what we can use SCAMP for, and where the whole world of interacting with focal plane sensor processors all the way to physical actuators is going.
Okay. Yeah, thanks. Actually, we are developing the next generation things, and I think we can make it public in the near future.
Awesome.